Hello. For this video, I will be discussing my solutions to the first part of the 28th Philippine Mathematical Olympiad. We start with the first problem. Let n be the sum of the reciprocals of 20 and 25. We're looking for the smallest integer that exceeds the reciprocal of n. I think this is perhaps the easiest question in the first part of the qualifying stage. So this is pretty straightforward. Write n as the sum of 1 over 20 and 1 over 25. We just find the least common denominator of this one, which in this case should be 100. And then express 1 over 20 as 5 over 100 and then 1 over 25 as 4 over 100. To get the numerators, you just divide the 100, the LCD, by that specific denominator. Simplify this to get that the value of n is actually 9 over 100. Hence, the reciprocal of n is 100 over 9. And we write that as a mixed fraction, or mixed number. That's 11 and 1 over 9. So the smallest integer that exceeds this value is actually 12. Okay, if you participated in the qualifying stage, I hope you got this question right, because this is, again, the easiest question in the qualifying stage. Next, we move on to the second question. Edita wants to run a kilometer in 4 minutes. In the first minute, she runs at 18 kilometers per hour. What constant speed in kilometers per hour must she maintain in the remaining 3 minutes to achieve her goal? Now for this one, we have to remember the formula for the distance. The distance covered is equal to the constant speed times time. Again, it's important to note here that it involves a constant speed. Otherwise, we will have to use more complex equations than this. But for the purposes of the problem, we're given constant speed, so this simple equation should apply. So the goal here is to find the speed, so we let that as x. The total distance that must be covered is 1 kilometer. So that's the eventual distances. And we split that distance into two. The first part being the distance she has covered in the first minute, and then the other is the distance she will cover on the next 3 minutes. On the first minute, her speed was 18 kilometers per hour, and then she covers that in 1 minute. So the distance covered is 18 times 1, but we divide it by 60 to make that to make the time in hours, right? So to be dimensional consistent, I suggest that you convert a minute into hour, and that's 1 over 60. Why 60? Because there are 60 minutes in 1 hour. Okay? Now for the second distance, the person must travel at a speed of x for 3 minutes. So the distance covered is x times 3 over 60. Right? So just combine this. We want the sum of the first and second distance to be equal to the target distance. So that's 18 times 1 over 60 plus x times 3 over 60 is equal to 1. Once you've established this equation, all that's left is to solve for x using simple algebraic operations. So we multiply both sides by 60 to remove the fractions. We get this 18 times 1 plus x times 3 equals 60. Isolate the variable on one side by subtracting both sides by 18. Then divide both sides by 3. Simplify to get that x is equal to 42 over 3, and that value is 14. So the speed that Edita must take for the rest of the time is 14 kilometers per hour. Okay? Again, this is fairly easy compared to the rest of the questions. So if you participated in the qualifying stage, I hope you got this right. Right? Next, we move on to the third problem. The diameter of a 1 peso coin and a 5 peso coin are 24 millimeters and 27 millimeters respectively. Suppose we lay down some 1 peso coins and 5 peso coins end to end, forming a line that is 18 centimeters long. We are asked to find the total value of the coins in the line in pesos. Okay, for this one, we let X be the number of 1 peso coins and Y be the number of 5 peso coins, right? So if you lay out some of the coins like this one, you have X coins as indicated in the gray ones, and then Y coins indicated in the silver, in the gold coins here. Okay. Now we're given that the diameter of the 1 peso coins is 24 millimeters, and that of the 5 peso coins is 27 millimeters. So the total distance, or the total length of this span right here, is equal to 24 times X. That's the number of coins, plus 27 times Y, which is the number of 5 peso coins. And this total length should be equal to 18 centimeters long. But to be dimensionally consistent, we're given here the diameters in millimeters, but the total span as centimeters. So we convert this first, the centimeters to millimeters, by noting that 1 centimeter is equal to 10 millimeters. So 18 centimeters should be equivalent to 180 millimeters. Right? I hope you got it. So this sum right here, 24x plus 27y, should be equal to 180. So what's left here is to find values of x and y that satisfy this equation right here. We only have one equation and two unknowns, so it is impossible to find exactly one solution for this one. Right? One equation, two unknowns, so it's practically impossible to pinpoint one solution. But we should note that x and y here should be whole numbers, because we're referring to counts of coins, and there are no negative number of coins, nor there is a fractional number of coins, right? So we will use that condition to identify which of the values of x and y that satisfy this equation are also whole numbers. Okay? So to simplify the computation or the analysis, we divide both sides of this equation by 3 to reduce the coefficients. 24x becomes 8x, and then the 27y becomes 9y. The right side becomes 60. At this point, you can just simply try all the values of x, all whole number of values of x, and look for the values of y that gives another whole number. That's okay. But just to further simplify the computation or the checking, I suggest that we do some filter by noting that the right side is 60 is divisible by 3, and 9y is also divisible by 3. So this 8x right here must be divisible by 3 as well, because if this 8x right here is not divisible by 3, then this left side will not be divisible by 3. So here we conclude that x must be divisible by 3. So this means that we only have to check the values of x that are 3, 6, 9, 12, and so on. Right? You get it? We can do similar check if you want to further narrow it down with the values of y. So we can check both sides that y and conclude that y must be divisible by 4. But this one is enough. It's enough to just check the numbers that are divisible by 3 for x. Okay, so we start with x equals 3. If we do that, we get the value of y as 4. So this is a valid solution because both of them are whole numbers. If we check 6, then it gives a y value of 4 over 3, which is not a whole number. So this is not okay. If we check x equals 9, we get a negative number, so that's not okay as well. If you increase the value of x, like 12, 15, then all the values you get are negative. So we conclude that the only solution here that are both whole numbers is 3, 4. So x must be 3 and y must be 4, which is exactly how I do it here. We have 3 1 peso coins and then 4 5 peso coins. Get it? We're looking for the total value, so we multiply the number of coins 3 by the value, which is 1. So this is 1 times 3, being the total value of the 1 peso coins, and then 5 times 4 is the total value of the 5 peso coins, which gives a total value as 23. So the answer for this problem is 23. Okay, I hope that's clear. Next, we look at the fourth problem. Circles A and B have the same center. Circle A has an area of 2025 pi square centimeters, and circle B has diameter of 28 centimeters. Circle C is tangent to both circles A and B, and we're looking for the sum of all possible radii of circle C. I hope you understand the problem. Before we actually look for the radius of circle C, I suggest that we first work on the radius of circle A and circle B, just to be consistent. We're given that the area of circle A is 2025 pi, and we know that the area of a circle is pi r squared. So if we let the radius of A to be r sub A, then we have 2025 pi is equal to pi r squared. You cancel the pi on both sides, and you'll get r of A is equal to the square root of 2025, which is 45. Right? Now, circle B is easier. We're given the diameter. So the radius is half of that. R sub B is equal to 1/2 times 28, which is 14. Okay. So now that we have the radius of A and B, we can now examine or determine what circle C should look like. Okay, so we first draw here the center of the two circles, A and B. The orange circle right here corresponds to circle A, and then the smaller one is circle B. Circle B should be smaller because it has a radius of 14. Now, there are only two possible orientations of circle C that is tangent to both A and B. One of this is like this one, the gold one, that is in the area between the two circles. So this is the point of tangency for circle B, and then this one is the point of tangency for circle A. Now the other orientation is like this one. So basically it encloses the smaller circle. Okay, let's examine first the smaller one. Let's determine its radius. Note that the distance from the center to the bottom of this length right here should be equal to the radius of circle A, which we know to be 45. And then we can split that distance into two. The first one is this space right here, which should be equal to the radius of circle B, which is 14. So the other distance should be 45 minus 14, right? And this distance right here should correspond to the diameter of this smaller circle. Let's call this um, small circle and its radius to be r sub small. So r sub small should be equal to half of 45 minus 14. Okay, let's not simplify that for now and keep it as it is, right? Now let's examine the other one, the big one. So this is the big one. Again, we can check some of the distances right here. We know that this upper part is the radius of circle A, so its distance is 45. And then the other one is the radius of the smaller one, which is 14. So the radius of, or sorry, the diameter of this big circle right here should be 45 plus 14. And therefore, the radius of that circle is 1/2 of 45 plus 14, right? So the sum of this radii is 1/2 times 45 minus 14 plus 1/2 times 45 plus 14 is equal to 45. It's quite easy because you have here minus 14 and then plus 14 right here, and that cancels out. That's why I asked you not to simplify this too earlier, because eventually you can simplify that out. And that advice is 2 in most cases. Generally, I suggest that if you have expressions like this, don't simplify it outright and then look further ahead and see maybe there's something about it that would make the computation easier in the end. Okay? Anyway, so the sum here, the sum of all radii here is 45. And that's our final answer. Right? I'm not sure if you've noticed, but there's an easier way to do this without actually looking at the radius of the individual circles. If we just step back a bit and draw the two circles, we note that the sum of the diameters of these two circles is just equal to the diameter of the red circle or the orange circle. So this total distance right here should be equal to 2 times 45. So this is the sum of the diameters. So if you want to find the sum of the radius, you just divide this by 2. So 2 times 45 divided by 2 is just 45. So if you figure that out, then this problem should be doable in like 15 seconds or so. Okay? I hope we're doing good so far. Okay, we look at number 5. When we add the measures of all the interior angles from 3 convex polygons, we get 3060 degrees. What is the greatest possible number of sides of the polygon that has the fewest sides? Again, this question is not particularly hard, but based on the comments I saw in the post where this was originally posted, or I mean, many students got confused here with the statement, greatest possible number of sides of the polygon that has the fewest sides. I understand the confusion, so I think it would be best if we look at that, what it meant later on in the solution. So just for now, bear with me with the first part of the solution, and later on we'll look at what exactly this question meant. Okay? Now to answer this problem, we should note that the sum of the interior angles of an n-sided polygon is equal to 180 degrees times n minus 2. So basically, if you have a triangle, n equals 3, so that's 180 degrees times 3 minus 2, which is 1, so 180 degrees. For a quadrilateral, which has 4 sides, total is 180 degrees times 4 minus 2, which is 2, so the total interior angles is 360 degrees. Okay, so if we let n sub 1, n sub 2, and m sub 3 be the sides of the three polygons, then the interior angle, the sum of the interior angles for the first polygon should be 180 degrees times n sub 1 minus 2. And then for the second polygon is 180 degrees times n sub 2 minus 2, and so on. The sum of these three should be equal to 3060 degrees, as was noted. Simplify this, we divide both sides by 180 degrees. The right side is divisible by 180 degrees. It should be divisible by 180 degrees. And if you divide that, we get the right side to be equal to 17. We isolate the variables on the left side by adding 6. So we get n sub 1 plus n sub 2 plus n sub 3 is equal to 23. Similar to the other problem earlier, this is a single equation with 3 unknowns, so it's quite impossible to actually figure this out. I mean, it's not actually possible to just pinpoint one solution for this equation. Now what we do is we examine the possible values of this one. Let's consider triples n sub 1, n sub 2, and n sub 3 that satisfy this equation. For example, the triple 3, 10, 10 satisfies this equation. There are actually other triples that has 3 as one side. You can have 3, 9, 11. That's another set. Then you can also have 3, 8, 12, and so on. But the important thing here is that there is a set that has 3 as the smallest side, right? Similarly, you can get the triple 4, 9, and 10, where the smallest one is 4. Again, there are other sets which has 4 as the lowest number of sides. The question in the problem is to find the lowest or the greatest possible value of this lowest value. So basically, it's like asking, is there a configuration, a triple where the number of sides, the lowest possible number of sides is greater than 4? How about greater than 5, greater than 6, and so on? So we check, is there a set that is greater than 5? I mean, is there a set where the smallest one is 5? The answer is yes. We have 5, 8, 10. Is there a set which has 6 as the smallest? Yes, there is. That's 6, 7, and 10. Is there a set which has 7 as the lowest? The answer is yes. That's 7, 8, 8. Is there a set where 8 is the lowest? The answer is no. Because if the lowest is 8, the total sum of the other two should be 15. And if the sum is 15, then the only possible, the closest set you'll get is just 8, 7, 8. But if that's the case, then 8 is not the lowest. 7 is the lowest. You can continue that argument with 9, 10, and so on. You cannot find a set where the lowest value is more than 7. So 7 here is what we conclude as the maximum. Right? So the answer to this problem is 7. And that's our final answer. I hope that's clear. If you're still not understanding or it's still confusing what's meant by this phrase right here, just let me know in the comment section, and then I'll let you I'll further explain if needed. Okay? Okay, let's look at number 6. If x, y, and z are positive real numbers such that log of x base 3 equals log of y base 5 is equal to log of z base 2025. Which of the following represents the value of z in terms of x and y? This problem is not particularly hard, I think. And the key here is to let these 3 numbers right here to be equal to a constant. Let's say they're equal to c. It follows that using the relationship between an exponential and a logarithm function, that x must be equal to 3 to the c. I hope that's clear. X is equal to 3 to the c. Then y is equal to 5 to the c. Then z is equal to 2025 to the c. Right? Right. Okay, so the goal is to express z in terms of x and y, which should be a bit clearer now because we are given everything that has an exponent of c in here. Right? We have here 2025 to the c, 5 to the c, and 3 to the c. We know that 2025 is equal to 45 squared, so this right here is equal to 45 squared to the c. And then we know that 45 is 9 times 5, which is 3 squared times 5. So this inside here is equal to 3 to the 4th times 5 squared. Right? 3 to the 4th times 5 squared. And this value is equal to 2025. I'm showing you the process of how I solved it. Technically, you cannot, you can skip this 45 square right here and then just straight out factorize 2025 like this one, but it's a personal preference. I know 2025 is 45 squared, so for me it's easier to factor it this way. Anyway, the important thing here is we know that 2025 is equal to 3 to the 4th times 5 squared. And then we just sort of use the product property of exponents. So it's equal to 3 to the 4th to the c times 5 squared to the c. And then we use the power of a power property. 3 to the 4th to the c is equivalent to 3 to the c to the 4th. And then the other one is equivalent to 5 to the c squared. But wait a minute, we know that 3 to the c is x. 5 to the c is y. So this expression right here should be equal to x to the 4th. This is y squared. So the answer here is x to the 4th y squared. And that's our final answer. Okay. As a general tip, if you're facing problems involving logarithms, I think it's a good idea to write the equivalent exponential equation of those logarithmic equations. Okay? Right. Okay, let's look at number 7. Let n be a positive integer greater than 9, and let a sub 1, a sub 2 until a sub n be a regular polygon with n sides. Suppose that the segments a sub 1, a sub 7, and a sub 2, a sub 9 intersect inside the polygon and form an angle of 15 degrees. The question is, what is n? So step 1, we draw a polygon. It looks like this. Label some vertices until a sub 9. And then draw the segment a sub 1, a sub 7, shown here in orange, and then a sub 2, a sub 9, shown in green. They intersect at a point inside this, that, and then the angle they form is 15 degrees, shown in gold. To aid us in solving this one, we draw a circle circumscribing the polygon, like the black one here. And we note that for this polygon, the central angle indicated by this purple pi right here, each measures 360 degrees over n. Because if there are n sides right here, basically you're dividing the whole pi into n pies, and then or n pieces, and that each piece should measure equally and equal to 360 degrees over n. And then we know that Each of these subtended arcs should be equal to the central angle. So each of these should measure 360 degrees over n, right? So each of this, like space right here, measures 360 over n. So this space right here, a sub 7 to a sub 9, should measure 2 times 360 over n. And then this one should measure 360 over n, right? And here comes the fun part. From geometry, we know that given two intersecting chords, the measure of the angle here should be equal to half of the sum of the two arcs. So this 15 degrees right here should be equal to 1/2 of a sub 7 to a sub 9, which is 2 times 360 over n, and then a sub 1 to a sub 2, which is 360 over n, right? So to remove the 1/2 here, we multiply both sides by 2. The right side becomes 30 degrees. And then this involves 360 over n, both of them. So this becomes 3 times 360 over n, the right side being equal to 30 degrees still. So we like cross multiply, cross divide to get n being equal to 3 times 360 degrees over 30 degrees. We cancel out the 30 here, 30, 30. So this is 12. 3 times 12 is equal to 36. So the number of sides of the polygon is 36. So the answer here is 36. Right? You get it? So the important part here, or the important tricks that we did here, is making use of this central angle measure here, and the measure of each arc, then using this theorem involving intersecting chords. Okay, so just one homework for you if you're watching and want to improve. In our illustration, we labeled this part here to be the angle 15 degrees because well based on our drawing, this is what it actually should look like. I mean, this is clearly the smaller angle between the two. But I want you to check, what if we set this angle to be the 15 degrees? Because there might be a configuration where, or there could be a configuration where this is the 15 degrees. You check that and see and prove to yourself that the resulting n for that case will not be an integer, and that the only answer here is actually just n equals 36. Okay, that's my homework to you, and please share your solution in or explanation in the comments. Okay? Okay, let's look at problem number 8. Points T, S, P, M, and O lie on a circle in clockwise order such that TS is parallel to PO and TP is parallel to MO. Let lines TS and PM intersect at point N, and we're given that PN equals 8, PM equals 12, and MO equals 30. We are asked to find the length of TP. I think this is a pretty standard problem. So when I first saw this problem in the comments, or I saw the comments to this problem, I was surprised that there are some curious explanations or comments from the people. Apparently, this TSPMO meant something for the Gen Z. So if you know that, then congratulations. As a millennial of my age, I'm not familiar with that one and just learned that thanks to this problem. So to the PMO team, thank you for teaching me this acronym right here. But anyway, we'll look at the solution for this one. As with any geometry problem, the first step right here is to first draw the diagram, which sometimes or many times probably is one of the hardest part of the problem. Okay, we first draw TS to be parallel to PO. So this TS, we draw it parallel to PO. And then we draw TP, so we have P here, parallel to MO. So MO should be here. And then we extend TS and PM like this one, so that they intersect at a point we call N. We're given that Pn equals, oops, I think I mislabeled this one. This Pn should be 8, and then PM should be 12. Sorry, this is a miss label. This should be, PM should be 12, Pn should be 8. And then the MO should be 30. Okay? So this should be 12, again, sorry, this should be 12, this should be 8. We put this on the side. We note that we have two pairs of parallel lines here, and whenever you have pair of parallel lines, it's likely a hint to you or to us that the problem should involve congruent angles using the corresponding angles theorem or same side interior angles theorem and so on. In this case, if we consider the transversal to parallel lines MO and TP, so this is the transversal right here. Oh, sorry, we consider MO and TP. We consider the line MN as a transversal. So this angle here and angle here indicated in green are or should be congruent, like by the corresponding angles theorem. And then on the other hand, if you look at the other pair of parallel lines, we have here, I think I mislabeled this one again. This should be, this angle here is congruent to this angle here. This OPM should be congruent to TNP. My bad for the diagram, sorry. There should be OPM. OPM should be congruent to TNP. Okay? Again, OPM, this side, this angle here is congruent to this angle here. My bad. I'll just post in the comments the actual correct diagram for this one. Okay, again, my bad. And then because we have two angles that are congruent, then by angle-angle similarity, we know that OPM should be similar to TNP. That's the angle-angle similarity theorem. Okay? So we know that they are similar. So by the definition or theorem about similar triangles, we know that the corresponding parts should be proportional. So in this case, we have OM over PM should be equal to TP over NP. Now we strategically selected this side because OM, PM, and NP are known, they are given, and then TP is what we're looking for. So if we solve for TP right here, we have TP equals OM over PM times NP. So you just multiply both sides by NP. And then you substitute the values. OM is 30, PM equals 12, and then NP is 8. Multiply that and simplify to get that TP measures 20. So the answer here is 20. Okay, again, my bad. I mislabeled this one. But anyway, the explanation holds the same. So basically, we use properties of parallel lines here and then use similar triangles. Okay. Okay. Let's look at number 9. The three cylindrical containers in the figure below have the same volume. Also, the containers contain the same amount of water. Furthermore, the water level in the first is as high as the second container, and the water level in the second container is as high as the third container. If the first container is 400 cm tall and the third container is 144 cm tall, how high is the water level in the third container? It's a good problem. I think this is a good problem. It's not hard, but it's an interesting one. So we let h sub 1 be the height of the first cylinder, and we know that to be 400 centimeters. And then we set h sub 2 be the height of the second cylinder. And we know also, based on the problem's description, it's that it's equal to the height of the first, the water level of the first one. And then h sub 3 be the height of the third, which we know to be 144. And we also know to be equal to the water level of the second one. And then the water level of the fourth, of the third, we let that as h sub 4. We will also call the radius of the cylinders as r sub 1, r sub 2, and r sub 3, but I did not write them here to avoid clutter in the diagram. Okay? We know that the volume of a cylinder, a right circular cylinder, is equal to pi r squared times height. Right? So the volume of the first one should be pi r sub 1 squared times h sub 1. For the second one is pi r2 squared times h sub 2, and so on. Since we know that they have equal volumes, then we know that pi r1 squared times 400 is equal to pi times r2 squared times h2, and so on. Right? This is the statement or the equation we get from the condition that they have the same volume. They have equal water, so we will use h sub 2 as the height of this one. It's like another cylinder right here. So it's pi times r1 squared times h sub 2. This is pi r2 squared times 144, and then the third one is pi r3 squared times h sub 4. Okay? Okay. Now let's consider the first side here, and then the second side. Note that if we divide the corresponding elements, we can cancel out the radius. So r1, r1, r2, r2. So if we do that, we get here that 400 over h2 is equal to h2 over 144. So we're just basically playing around the properties of equality, right? We just divide corresponding sides of the equations. So if we cross multiply, we get 400 times 144 equals h sub 2 squared. To get h sub 2, we get the square root of this product. So this is the square root of 400 times 144. Don't multiply these two. It's going to take you some time, and getting their square root will make you also spend some more time. To actually evaluate the square root, you first get the square root of 400, which is 20, square root of 144, which is 12. So the value of h sub 2 should be 20 times 12, which is 240, right? Okay. Next, we use the second and the third one to conclude that, first one and the last one, 400 over h2, which we know to be 240, and then it's equal to 144 over h4. Again, we equate that. We solve this equation similar to how we solved it earlier. Cross multiply and then divide both sides by 400. We get that h sub 4 is equal to 86.4. Okay, I hope that's clear. Right? So basically, we just set up equations for volume equality, and then we do the same for the water level, or the water volume. Okay, so the answer here is 86.4. Right? Right? I hope that's clear. Okay, last problem. How many non-empty subsets of 1, 2, 3 until 10 are there such that the product of the elements of S ends in 0? So this is the first combinatorics problem in the part 1. So to answer this problem, we have to note that, or to make use of the the consequence of the fundamental counting principle that the number of subsets of a set with n distinct elements is 2 to the n. Basically, if you're not familiar with this one yet, this is basically the case because for each of the n elements, they are either in the subset or not in the subset. So for each of the 10 elements, you have two possible ways of including or excluding them, right? So multiply n times, you get 2 to the n. Okay? To answer this problem, we will use complementary counting, meaning we count first the total number of subsets, and then we subtract the case that we don't want. Now, the case that we want, the subset that we want, should contain at least one multiple of 2 and one multiple of 5. That's the only way that the product will end up with digit 0. Okay? Now, the total number of subsets, because this has 10 elements, is 2 raised to 10. Now, from this total subset, we will subtract the cases we don't want. And the cases we don't want are those that does not have multiples of 2 and multiples of 5. So, the number of subsets without multiples of 2 should be 2 raised to n again. But in this case, n should be 5 because out of the 10 elements, 5 are multiples of 2, like 2, 4, 6, 8, and 10. So only 5 are not multiples of 2. So the number of subsets without multiples of 2 should be 2 to the 5. Right? I hope that's clear. Now we apply the same reasoning to exclude the number of subsets without multiples of 5, and that's 2 raised to 8. Because out of the 10 elements right here, only 5 and 10 are multiples of 5. So the rest, 8 of them, are not multiples of 5. So from the total of 2 to the 10, we will subtract 2 to the 5 and 2 to the 8. Because, again, they are the cases where they don't have a 2 or a 5. Right? Now, if you calculate this one, you'll get the answer to be 736. And that's part of the decoy of the organizers, the PMO team. They want you to answer this one, the 736, but that's wrong. Because remember that if you do complementary counting, you should avoid overcounting, the overlaps. Because in this case, you are counting subsets that does not have multiples of 2 and subsets that does not have a multiple of 5, but it's possible that some of these subsets actually have already been counted in the other one. Like for example, if we're talking about 1, 3, the subset 1, 3, it does not have a multiple of 2, it does not have a multiple of 5. So that subset would have been counted or was counted here in the first one and also counted in the second one. So we must add back those subsets, right? You get me? This is what is commonly referred to as the principle of inclusion and exclusion. The general idea is to avoid overcounting. So in this case, we want to add back the overlap, which is the case when the subsets do not have multiples of 2 and multiples of 5. Out of these 10 elements, 5 are multiples of 2 and 2 are multiples of 5. But we've already have counted 10. So the only ones that are not divisible by 2 and 5 are 1, 3, 7, and 9. So there are only four. So the number of subsets for this last one should be equal to 2 to the fourth. And that's what we add back here. So the value of this, or the number of subsets required, is this minus this minus this plus this, which is 752. And that's our final answer. Okay? So this question, I think, for me, this is the hardest question in the part one. And many students, I think, are not comfortable yet with the idea of complementary counting and principle of inclusion and exclusion, which are important topics or techniques that you have to learn in order to be, or for you to be able to answer combinatorics problem. So let this problem be like an introductory or a guide for you, a reminder to you that it's important to know the complementary counting and inclusion exclusion. Okay, so it's quite a long video because I tried to explain these 10 problems in just one set. Thank you for bearing with me. I hope you learned something from me today. If you have any questions, comments, or violent reactions, just let me know in the comments. Thank you for watching and see you on the next one. Bye bye.